Hello everyone, so for today we are going to continue our tutorial discussion with 8.4 Conservations of Angular Momentums. So as we already learned in chapter 3, in linear motion, any object with velocity or moving have momentum p. P is equal to mv. So in rotational motions, any body that have ability to rotate will also have what we call angular momentum, L. So how we find the angular momentum for a rotating object? So the angular momentum for a rigid body is given by L equal to I omega, where I is the moment of inertia, omega is what we call angular velocity or angular speed. If we just consider a particles on a rigid body, for example, this one, if we just consider a particles on a rigid body and this particle is at a distance r from the axis of rotation, normally when the rigid body rotates, this particle will move in a circular path and it will have tangential velocity v. Then this particle will have angular momentum, which can be calculated using these equations. The angular momentum for this particle is given by L equal to mrv, or we have mr squared omega. So please kindly distinguish these two equations carefully. So L equal to I omega is the equation we use to calculate angular momentum for rigid body. But if we want to just focus on a particle on the rigid body, then the angular momentum will be calculated using mrv, whereby m is the mass of the particle, r is the distance from the axis of rotation, and v is the velocity of the particle. So the SI unit for angular momentum is kg meter squared second minus 1. Since like linear momentum, angular momentum L is also a vector quantities. Okay, then class, if you still remember, in chapter 3 we have conservations of linear momentum. So same goes for rotational motion. In rotational motion, we have conservations of angular momentum. If no external torque acting on a system, we will find out that the total angular momentum of a system will always remain constant. What is meant by remain constant? Remain constant means the initial angular momentum will always equal to the final angular momentum. This means that if initially I have 250 kg meter squared second minus 1 angular momentum, then final I must also have the value of angular momentum equal to 250 kg meter squared second negative 1. So the value of angular momentum initial must equal to final. This is what we call conservation of angular momentum. The value of angular momentum is always remain constant. Okay. So since we know that L is equal to I omega, so we can rewrite the above equation whereby L initial will be moment initial multiplied with the angular velocity initial. angular momentum final will be moment initial final multiplied with the angular velocity final. So, from L equal to I omega, if we rearrange the equation, we are going to have angular velocity omega equal to L over I. So according to the conservations of angular momentum, our total angular momentum is always remain constant. So if L is constant, we will find out that our angular velocity omega will be inversely proportional to the moment of inertia I. So in other words, as the moment of inertia I change, the angular velocity omega will change. It means that as you increase the moment of inertia of the system, then the angular velocity will decrease such that our angular momentum will always constant. If we decrease the moment of inertia of the system, then our angular speed or angular velocity will increase. Okay? So you can see clearly from the equations, as our moment of inertia I change, our angular velocity omega will change. For example, this one, initially we have a merry-go-round with a moment of inertia 500 kg meter squared is rotating with the angular velocity 2 radian per second. Okay, then what happened? Let's say we put a box on the merry-go-round. So this will increase the moment inertia of the system because the mass increases for the system. Let's say now our moment of inertia I changes from 500 kg meter squared to 600 kg meter squared. So because the I went up, our I went up, increased, so the angular velocity omega of the merry-go-round have to decrease. So how we can find the new angular velocity or the final angular velocity of the merry-go-round? So we can find the new angular velocity using the conservations of angular momentum. Okay, we know that according to the conservation of angular momentum, I initial omega initial must equal to I final omega final. So we put in the value. Our I initial is 500. Our initial angular velocity is 2 radian per second. Our I final is 600. So what is our final angular velocity or the new angular velocity? After we put a box on the merry-go-round, we can calculate and we will find out that the final angular velocity will be 1.6 radian per second. So you will find out that when your I increases, our angular velocity will decrease. Okay, so basically the conservations of angular momentum is used by many athletes, acrobats and gymnasts. For example, if we consider this ice skater, as this ice skater outstretches her arm, you will find out that our moment of inertia I is large. So our omega angular velocity will be small. Anyhow, when the ice skater pulls in her arm towards her body, it will decrease the moment of inertia. the I will become small. So what happened to the angular velocity? The angular velocity omega will become larger, and then the I scatter can spin faster. So this is one of the applications of angular momentum. Another example is the sport diving. This one. As the diver jumps off the diving board, a torque is produced by his weight, and it will cause the diver to rotate. So, how the diver can make few rotations in the air? So, when the diver curves up his body, it will bring his limb closer to the axis of rotation. Like this picture, like given in the picture, then we will find out that the moment of inertia I is reduced. So when the I reduce, our angular velocity omega for sure will be increases. So it will spin faster and able to make few rotation in A. Anyhow, before the diver enter the water, it will stretching out his body. Why? Because as it's stretching out his body, the moment of inertia I will be increases, and the angular velocity omega will be decreases. This will slow down the rotation rate. So there will be less water splash as the diver enter the water. Okay, so this is the two example or two applications of angular momentum. So boys and girls, by referring to these two applications, actually you can answer question 13A and also 15A in your tutorial 8. So for the next one, we are going to go through the questions in tutorials. We are going to see how we are going to apply the equations of angular momentum and also the conservations of angular momentum.